Welcome to GeoVenture. If you love exploring our amazing planet, make sure to like this video and subscribe to the channel for more awesome science adventures. Hey there, science fans. Let's talk about something really cool. I mean that literally, we're talking about ice ages. Now, when you hear ice age, you might picture a woolly mammoth trudging through a blizzard or a squirrel burying an acorn. But an ice age is so much more. It's a long period when Earth's climate gets significantly colder. We're not just talking about a few chilly winters, but deep freezes lasting tens to hundreds of thousands of years. Massive ice sheets called glaciers spread from the poles and cover huge chunks of continents. Imagine a giant ice cube, miles thick, slowly creeping. That's a glacier. At the last peak, about 20,000 years ago, ice covered most of Canada, the northern US, and much of northern Europe and Asia. Places like New York, Chicago, and London were buried under mountains of ice. The world looked incredibly different. Oceans were lower, and climates were colder and drier. Here's a surprise. Technically, we are living in an ice age right now. Geologically, anytime large permanent ice sheets exist at both poles is an ice age. And we have Antarctica and Greenland. We're in a warmer interglacial phase. Earth cycles between long, cold glacials and shorter, warmer interglacials. It's our planet's pulse. Glaciers advance, then retreat. Now let's explore what causes that rhythm. So how do we know all this? Science is awesome. Scientists are like detectives. They search for clues left behind. Scratches and ridges carved into bedrock. Glaciers carved deep U-shaped valleys and fjords. They scooped out the basins of the Great Lakes and dropped huge boulders, glacial erratics, far from their origins. By matching rock types, geologists trace the path ice took, like a breadcrumb trail. Then there are ice cores, long cylinders drilled from Antarctica and Greenland. Ice builds layer by layer, trapping tiny bubbles of ancient air, frozen time capsules. Labs measure those gases to reveal past CO2 and temperature changes. Ocean mud holds microscopic fossils. Their chemistry tracks ocean temperatures over millions of years. Put together carved valleys, erratics, ice cores, and fossils, and you get a rock-solid picture. Earth cycles through freezing and thawing. So what flips the switch from cozy to frozen? Time for a cosmic dance. One main driver is a grand celestial dance. Earth's orbit isn't perfect or unchanging. It wobbles, it tilts. Its path stretches and shrinks over vast timescales. Milankovitch showed how these orbital changes pace the ice ages. It's all about solar energy, how much sunlight different parts of Earth receive. First, eccentricity, the shape of Earth's orbit. It cycles from nearly circular to more elliptical every approximately 100,000 years. When the orbit is more elliptical, Earth spends part of the year farther from the sun, reducing energy slightly, like roasting a marshmallow. Hold it farther from the flame for part of each turn, and it cools a bit. That tiny change lines up with the 100,000-year rhythm of glacial and interglacial periods. The slow stretching of Earth's path can set the stage for ice to build. Not sudden, gradual, predictable shifts in the energy we receive. Think of eccentricity as the first crucial piece of the Ice Age puzzle, a cosmic wobble that sends shivers down our planet's spine. Planetary science at its grandest scale. Next, tilt. Earth is tilted about 23.5 degrees. This gives us seasons. Tilt toward the sun is summer, tilt away is winter. Over about 41,000 years, tilt rocks between roughly 22.1 and 24.5 degrees. Greater tilt means more extreme seasons. Smaller tilt means milder seasons. For glaciers, cool summers matter most. Snow must outlast the melt. Year after year, snow piles up, compresses, and turns into thick ice. It's like saving a little each month. Small deposits add up to a continent-spanning glacier. Then there's precession, a slow wobble over 26,000 years that changes the timing of seasons. Today, northern summers occur when Earth is farthest from the sun, making them milder. In approximately 13,000 years, they'll be hotter. Eccentricity, tilt, and precession sometimes reinforce and sometimes cancel, redistributing sunlight across the globe. This intricate dance sets the tempo for the ice ages. Milankovitch explains sunlight distribution, but the sun itself also varies slightly. The 11-year sunspot cycle changes output by a fraction of a percent, too short to cause an ice age. Longer lulls, like the Maunder minimum, coincided with the Little Ice Age's colder winters in Europe. Small solar changes can matter in a sensitive climate. Sometimes a feather is enough to tip the scale. A faintly dimmer sun plus cool summers from low tilt could be a powerful 1-2 punch. Volcanoes can cool the planet. Sulfur dioxide forms aerosols high in the stratosphere, spreading a hazy sunshade. After Mount Pinatubo in 1991, global temperatures dropped about 0.5 degrees Celsius for a couple of years. Sustained frequent eruptions over centuries could keep that haze, driving gradual global cooling. Short-term cooling comes from sulfur aerosols that rain out in years. Long-term volcanoes add CO2, which warms. To kickstart glaciation, the immediate sun-blocking cooling is what matters. When orbital cycles favor cool summers and volcanoes dim sunlight, their combined effect can help ice sheets grow. A whisper from our star, a veil from volcanoes, small nudges with big consequences. To grasp cooling, remember what keeps us warm: the greenhouse effect. Gases like carbon dioxide, methane, and water vapor trap heat, our cozy atmospheric blanket. Without it, Earth averages about -18 Celsius, not the pleasant 15 we enjoy. Ice cores show CO2 rising in warm interglacials and falling in glacials, almost in sync with the cycles. Colder oceans hold more CO2, like a cold soda keeping its fizz. As orbital cooling chills oceans, they absorb CO2, thinning the greenhouse blanket and amplifying cooling. Positive feedback: more ice reflects more sunlight, causing more cooling, which grows more ice. At the same time, falling CO2 fuels further cooling, letting oceans absorb even more CO2. Together, these loops turn a small nudge into a big freeze. Based on natural cycles, another glacial would eventually arrive, over thousands to tens of thousands of years. But we've changed the game. CO2 today is higher than in at least 800,000 years. Human warming now overwhelms the gentle orbital cooling. Models suggest we've likely delayed the next ice age by 50,000 to 100,000 years. Thanks for watching GeoVenture. If you enjoyed this video, please like and subscribe to our channel for more amazing science adventures. See you next time.